So in this video we're going to look at four results for the limits of sequences of real numbers that together are known as the algebra of limits. So let's say that we have two sequences which we'll call an and bn, and let's say both of these sequences are convergent, so they have a limit. So we'll say that the limit of the sequence an as n tends to infinity, we'll call that a, and likewise for the limit of bn as n approaches infinity, it's also going to be convergent, and we'll say that it converges to a limit b. So we can now write down these four results. So the first one is that if we consider a third sequence that is made by adding all of the terms of the two sequences together, so sequence an plus bn, and just to make sure that it's crystal clear what this means the first term of the sequence is going to be a1 plus b1, the second term will be a2 plus b2, the third term will be a3 plus b3, etc. So you just add the corresponding terms from the two sequences an and bn. So if we then think about, one, does this sequence converge, and two, what does it converge to? So hopefully you have some intuition about this. So if we draw a little picture, if we imagine the two sequences, let's draw the sequence A in green. So maybe it looks something like this, and it's converging to some limit here that is A, so it's getting closer and closer and closer to that. And then if we have the sequence B here, let's say it's converging to this limit B here, so all these terms are getting closer and closer to that. Then if we add these two together, corresponding terms together, so we add the first one of A and the first one of B together, the second one of A and the second one of B together, then we're going to get some third sequence that will show in red here, so we're going to be higher up, and the terms of this sequence are again going to get closer and closer and closer to some value, and that, hopefully you agree, is going to be A plus B. So this is the first result of the algebra of limits, that if you add two sequences together that are both convergent, that the third sequence is convergent and converges to the sum of the limits. So the limit of the sum of two sequences is the sum of the limits. Next, so I'm going to write down all four results, and then we'll discuss how important this is, and then we'll go through proving all four of them. So second result is that if we now take a constant, so let's say lambda is some constant in the real numbers, and we create a third sequence by just taking one of them, and we'll just take A rather than B. So we create this third sequence by just multiplying every term of the sequence by lambda. So this third sequence looks like lambda A1, lambda A2, lambda A3, etc. Then again, this is very intuitive. What's the answer as to what this converges to? Firstly, does it converge? The answer is yes, we'll show that. And secondly, what does it converge to? Hopefully you agree that it will just converge to lambda times the limit of the original sequence, so lambda times A. So there's result number 2. And now we're going to multiply sequences together and then divide sequences to get the two final results. So next result is, what if we multiply an and bn together, where an and bn are both convergent sequences. So again, this means a1, b1 is the first term, a2, b2 is the second term, a3, b3 is the third term. Is this new sequence, the product of the two previous sequences, is this convergent, and what does it converge to? Well, again, the answer is yes, it is convergent if a and b are both convergent sequences, and it converges to just the product of the limits. So the limit of the product of two sequences is the product of the limits. And then finally, the final one's a little bit more complicated to write because we have to worry about division by 0 potentially. So if we have a limit as n approaches infinity of an divided by bn, so here we need some conditions. We need bn to not equal 0, so none of the terms in the sequence, this sequence B, are allowed to equal 0, because of course then the corresponding term of this third sequence wouldn't be defined. So that's one of the conditions we need. We're also going to need the fact that it doesn't converge to 0, so this thing that we're dividing through by, this sequence, it can't converge to 0, otherwise we're going to have problems as well. This law isn't going to hold. If those two things are true, so none of the terms of the sequence are 0 and the overall limit of the sequence isn't 0, then it is true that this converges, and it will converge to just the limit of the sequence A divided by the limit of the sequence B, so just A divided by B. So those four results that we've got there, together they are known as the algebra of limits. These results hold all over the place, so we're looking at the moment at the starting point for the discussion of limits, which is the limits of sequences of real numbers. However, the concept of a limit extends to all sorts of different things, and these results hold true in all these other contexts, or they will have to prove that separately, but in many of these contexts, these results are going to continue to hold true. So the algebra of limits can refer to these same rules in lots of different contexts. Here we're looking at them in the context of sequences of real numbers. Now these rules are very useful because if we, for instance, want to work out, let me give you an example, the limit as n approaches infinity of some sort of rational function, let's have 9n squared minus 7n plus 8 divided by, or what will work nicely, let's have 3n squared plus 9n plus 10. I hope this is going to work nicely. So intuitively, if we want to know what the limit of this is a sequence. You can put in n values here, so we could actually try and work out some of the first terms of this sequence. So if we wanted to work out the first one, I'm already regretting even starting this, but let's do it now. So the first one is going to be 9, so we stick in 1 here, so that's 9, minus 7, that's 2, plus 8, so it's going to be 10, and I'll just write it as a fraction to make it easier. So 10 over, and then we'll have 3 plus 9, that's 12, and then plus 10. So that goes to 22. So that's the first term. Then the second term, can I be bothered with this? We'll do one more term. We'll do the second term. So it's going to be 9 times 2 squared, which is 4. So that's 36. Minus 2 times 7, which is 14. So we have 36 minus 14, that will make 22. Plus 8, that's 30. And I apologise if any of the mental arithmetic goes wrong here, but you get the idea. So 3 times 4 is 12, plus 9 times 2 is 18, so that goes to 30, plus 10, that's 40. So it goes on, you can work out all of these values. So it's a nice sequence. And what does this converge to? It does converge to something. The intuitive way to see immediately what this converges to is as n gets bigger and bigger and bigger, the n squared terms are going to grow at a faster rate, at a rate n times faster than the quadratic terms are going to grow a lot faster than the linear terms. So they're going to dwarf these linear terms, and these linear terms are actually going to become pretty irrelevant. So the top number really will just become 9n squared, and the bottom number will really just become 3n squared. So really, the ratio between the numerator and the denominator is going to converge to just that ratio between 9n squared and 3n squared, which is just 9 over 3. So the limit of this is 3. But we can prove that now using these results without actually having to resort to the full-on epsilon definition of a limit, because we're going to prove these results from the epsilon definition of the limit. So once we've done that, we will be able to apply that to this and it will constitute a proof that this thing's limit is what we overall get from using these results, because they came from the epsilon definition of the limit. So we won't have to actually resort to the epsilon definition of the limit to prove that this limit is free. So how do we do this? Well, firstly, there's a trick. And the trick is that we're going to multiply both top and bottom by 1 over n squared. So we're going to rewrite this. Limit as n approaches infinity of, and then I'll just go straight into it. So we'll divide through by n squared top and bottom. So 1 over n squared is always going to exist because we're starting with n is equal to 1 and going onwards. So it's never going to have the problem of dividing through by 0. So it will always exist. So it's a completely valid algebraic manipulation. And because we're multiplying top and bottom by it, we're not actually changing the value of the expression at all. So this is just going to become 9 minus 7 divided by n plus 8 over, oh whoops, first mistake, so that should be 8 over n squared. We've gone horrifically wrong otherwise. And then it's going to be over 3 plus 9n divided by n squared, which is 9 over n plus 10 over n squared. So we've just multiplied throughout by the multiplicative inverse of n squared. And you can see, if we put in n is equal to 1 into here again, we'll get the same answer as here, and n is equal to 2, we'll get the same answer here. So we haven't actually changed the value of this. This is exactly the same as what's up here. It's just a nice algebraic manipulation. And the reason we've done this is because we already know what the limit of the harmonic progression is. We proved that in our previous video where we looked at the epsilon definition of a limit. We showed that using that definition we can prove that the limit of this sequence is 0, so that's the sequence 1, a half, a third, a quarter, a fifth, a sixth, a seventh, etc. And now these things are all related to this, and we can use the algebra of limits now to reduce it down to just needing to know this limit. So let's do that. So algebra of limits then now. So we're going to split this up firstly into the limit of this divided by the limit of this using this rule here. So we should check these things here. Firstly, the limit of this thing on the bottom is going to be 3. Well, I need to give a bit of argument for that. So the problem is I'm going to use this argument later on to split it up. So we'll come back to proving that it meets those requirements, but we're going to split it up into top and bottom. So is equal to, I just don't want to end up repeating myself unnecessarily, so we'll come back to that. 9 minus 7 over n plus 8 over n squared divided by the limit as n approaches infinity of this thing on the bottom, 3 plus 9 over n plus 10 over n squared. So that's by this rule here, which we will prove. That's what we're going to do after I finish with this example. And then we're going to split each of these up using the addition rule. So we'll split this up into the limit as n approaches infinity of 9 minus the limit of this thing plus the limit of this thing. Minus can be pulled out after all because it's just multiplication by minus 1. Excuse me. So this will become, and I'll write a little bit more of this out. So limit as n approaches infinity of 9, which of course is just equal to 9. And then we'll have minus, and then we can pull that constant out. So we'll pull the 7 out. Limit as n approaches infinity of 1 over n. And I'm just going to make a bit more space. Plus, and then again we'll pull the 8 out. So 8 times, and now we're going to do another application of the algebra of limits. We're going to split up 1 over n squared into 1 over n times 1 over n. So it's an is 1 over n and bn is 1 over n. So we can now say that it's going to be equal to the limit of 1 over n squared, which I'll write out as 2 separate things so that it doesn't look confusing. So limit as n approaches infinity of 1 over n times the limit as n approaches infinity of 1 over n. I'll put some brackets here. And then we'll do the same thing to the denominator. So we'll have the limit as n approaches infinity of 3 plus 9 over 9 times the limit as n approaches infinity of 1 over n, plus 10 times the limit as n approaches infinity of 1 over n, all of that squared, so I've written it differently this time. So rather than writing this times this, I've actually just written this thing squared. And now, we know the limit of a constant sequence, so this is just the sequence 9, 9, 9, 9, 9, its limit is 9. We know what these limits are, they're equal to 0, so all of these things just cancel off. 0 times 0 is 0, so all of these things go, and we just end up with that it's 9 over 3, which is 3, as we said earlier on. So there we go. All we needed in order to analyse this limit was to know this thing's limit, which we've proven already using the epsilon definition. And then if we have proven all the results of the algebra of limits, then we don't actually need to resort to the epsilon definition to prove this thing's limit is equal to 3. We can use these rules. So I said I would come back to making sure that it fulfills these criteria. So let's go over that. So this thing here, hopefully you can appreciate that none of those terms are ever going to equal 0, because I chose the numbers carefully so that we wouldn't have that problem, because we've got 3 here, we've got always a positive number there because n is a positive number, and then we've got a positive number here as well, so this is just going to be positive. It's never going to somehow end up being 0, so yay, we're saved that, having to worry about that small little complication. And the limit of it wasn't equal to 0 as well, because if we look at the limit of this, it's just equal to this thing on the bottom. So that's why I didn't want to go through it earlier, because I felt like I was ruining what we were going to do later. So we again just split it up using the algebra of limits. It's the limit of 3 plus 9 times the limit of 1 over n plus 10 times the limit of 1 over n squared. So it's overall just equal to 3. So it did meet both of those criteria. So that's how useful these algebra of limit rules can be. We can work out rigorously what limits are going to be equal to of functions like this using these rules. So now the real fun begins. Let's prove these results, starting with the sum of the two sequences. So we want to start with these two things and arrive at a proof of this. So to prove that the limit of this third sequence converges to this is to show that the terms of this sequence get to and stay indefinitely close to this value. And the way we're going to get that is by the fact that the terms of this sequence get to and stay indefinitely close to this, and the same for this one over here. So we'll go over here for the proof. So we're going to take a general epsilon then, so let epsilon be greater than 0, and I want to show that I can find a big N such that for that big N and for all the terms after it, that the terms in this sum, an plus bn, are then within epsilon proximity of that limit a plus b. So let's think about what the difference then between the terms of the sequence, so an plus bn, and the limit a plus b are equal to. So it's equal to this. We want to show that we can find a big N such that from that big N and for all the terms onwards, this inequality is true. The way we're going to actually proceed is to apply the triangle inequality. The triangle inequality is a wonderful thing that we use all the time in problems like this. So we're going to slightly just rewrite this. So we'll rewrite this modulus initially as an minus a plus bn minus b. The reason being is we know we want these two things next to each other because we know something about the difference between an and a and bn and b. We know that we can make it indefinitely small and it will stay indefinitely small. Obviously at the moment we haven't quite got this in the form of mod of an minus a and mod of bn minus b. It's still one big modulus. However, we can now apply the triangle inequality, which in the real line is the inequality mod of x plus y is less than or equal to mod of x plus mod of y. And here we're going to let x be this bit and y be this bit. So we can now say that this is less than or equal to mod of an minus a plus mod of bn minus b. And that's brilliant because we now know something about these things. We've got it written in terms of things that we know something about. However, we want to make this less than epsilon. But the brilliant idea here is if we were to make this thing less than epsilon, so the sum of these two things less than epsilon, then this would automatically be less than epsilon by transitivity because this is less than these two things added together. So if we were to make these less than epsilon, then this would also be less than epsilon. So that's how we're going to proceed. So now we use the fact that the limit as n approaches infinity of an is equal to a, and the limit as n approaches infinity of b of n is equal to b. So what we can now do is apply the definition, the epsilon definition of limit, and we can use it with epsilon equal to our initial epsilon over 2. So I've been given an epsilon here, a general epsilon, that I've been asked to find a big N such that for that big N and for all the terms afterwards, this inequality is true. I'm now going to use the fact that I know these things are true on an epsilon equal to epsilon over 2 for both of them. So by the definition of the limit of this sequence an being equal to a, it means that there will exist some big N1, which is an element of the natural numbers, such that for all little n greater than or equal to that big N1, mod of an minus a will be less than epsilon over 2. So all I'm saying is that there will be a point in this sequence, we'll call that the big N1 term, such that for that term and for all the terms afterwards, the difference between the terms and the limit is less than this number epsilon over 2, because this is some number greater than 0, so by the definition of the limit, I can do this. Now I'm going to do the same thing for this sequence Bn, so there will exist, we'll call it big N2, because it's not necessarily the same as big N1. In fact, it's highly unlikely to be the same as big N1 in general. So there'll exist some big N2 such that for all little n is greater than or equal to big N2, mod of Bn minus b is less than epsilon over 2. So again, there will exist a point in this sequence where from that point onwards, the distance between the terms and the limit is less than this value that I'm trying to make it less than, which is epsilon over 2. And the reason that I want both of these to be less than epsilon over 2 is so that when I sum them together, it's less than our original epsilon. So that's where the epsilon over 2 has come from. So just to draw a picture, we've got our sequence A, A1, A2, and then we go along to some A big N1, and then from that term onwards, all of these terms are a distance less than epsilon over 2 from the limit A. So in the real line, if we have our limit A here, there's then some tiny little epsilon over 2 interval here. So this is epsilon over 2 plus A, and this is A minus epsilon over 2, the lower boundary of that interval. And all of these terms are going to be inside that interval. Likewise for the sequence B, we've got B1, B2, and then we go all the way up to Bn2. Now, I'm saying in general n1 is not going to be equal to n2, so one of them is going to be bigger than the other. For the sake of the picture, I'm assuming it's the n2 one that is bigger than the n1 one. However, in general, it could have been the n1 one that is bigger than the n2 one. But one of them is going to potentially be the biggest. Either that or they're actually equal to each other. But in general, one is going to be bigger than the other. So on this picture, it's B. And again, in the real line, we have our limit B, we have our interval of radius epsilon over 2, so B minus epsilon over 2 is the lower limit, and all of these terms of that sequence are then going to be inside there so that the distance between them is less than epsilon over 2. Now, if I then looked at the corresponding term in the A sequence, so the AN2, so I'm assuming this one is the bigger one, I'm saying go along to that term AN2, which is after the term A big M1. It's still going to be true that for that term and all the terms onwards, that they're going to be inside there. So here's now the final idea. If I have my third sequence, which is A1 plus B1, A2 plus B2, and I go all the way up to this equivalent term, A big N2 plus B big N2, then my claim is that from that term onwards, all of these terms of the sequence are going to be within a distance of epsilon of the limit A plus B. So for the picture, here's our limit, and I claim now that all of these terms are going to be inside that interval, so this is now the epsilon interval, so A plus B plus epsilon and A plus B minus epsilon. And the reason is that we can apply this inequality up here. So the distance between these terms and this limit is going to be less than or equal to this bit. Now, for all of these terms onwards, we've said that the distance between them and their limits is going to be less than epsilon over 2. So this one is less than epsilon over 2. This one is less than epsilon over 2. So clearly, therefore, the sum of the two of them is less than epsilon, but this thing is then less than that sum. So by transitivity, this thing is certainly going to be less than epsilon. And that's the reason that I've had to take the maximum of the M1 and the N2s and take that as my big N for my third sequence. Because if we'd used the smaller one, say we'd started down here, if we'd started at B big M1, well then it wouldn't be true necessarily that for all the terms of that sequence from this one onwards, that they would have been inside that epsilon over 2 interval. That's why I took the larger one, because it would then be true in the other sequence that for that term and all terms onwards that they'd still be inside the epsilon over 2 interval. So that's the idea of that proof then. So you have your general epsilon and you now just make the big N equal to the maximum of big M1 and big N2, where big M1 and big N2 are the natural numbers that were necessary to make all the terms of the sequence beyond them less than epsilon over 2 for our original sequences AN and BN that we wish to sum. So that's how you can find your big N. If they were the same number, of course, then the maximum is just, that same number. But in general, one will be bigger than the other, so take that bigger one, and then that will do as your big N, and you then have a proof that for all of those terms in your third sequence onwards, and that the distance between them and the limit will be less than this epsilon. And since we did this for a general epsilon, we can then say for all epsilon greater than 0, it is true that there exists a big N such that for that term and all the terms onwards, the distance between the terms and the limit is less than that epsilon. So there we go, there's that proof. So the other three are going to follow using pretty much the same sort of argument. The next one is going to be the easiest, and then the final two are going to be a little bit more complicated. So next we want to prove that limit as n approaches infinity of lambda times an is equal to lambda a. So again, what we need to do is let epsilon be greater than 0, and we need to show that we can find a big N such that for it and for all the terms beyond it, the distance between the terms of the sequence and the limit, lambda a, is less than epsilon. And so how are we going to proceed with this? Well, we're just going to pull that lambda out of there. So by the property of the absolute value function, this is just going to be equal to the modulus of lambda times the mod of an minus a, and we need to show that we can find a big N such that that is less than epsilon. Well, now this is easy, so we just need to find a big N such that mod of an minus a is less than epsilon over mod of lambda, it should be, not just lambda. So let me erase that, over mod of lambda. So of course you can do that because we know that the limit as n approaches infinity of an is equal to a. So just use now epsilon over mod of lambda, which is some tiny little number potentially. Use that as your epsilon in this definition. Because this converges to this, there will exist some big N such that for that term and all the terms beyond it, all of them are within epsilon over mod of lambda of a, and therefore you can carry that big N over to here and use it as your big N, and this inequality will then hold that the terms of this sequence are less than epsilon distance away from the limit lambda a. So very nice simple argument there. So let's move on to the more difficult ones then now. So next up is we want to show that the limit as n approaches infinity of an times bn is equal to a times b. So again, take a general epsilon, so let epsilon be greater than 0, and we want to show that there exists a big N such that for it and all the terms afterwards, the difference between the terms of the sequence and the limit is less than epsilon. So what is the difference between the terms of the sequence and the limit? Well, it's equal to an times bn minus ab, and we need to show that we can make this less than epsilon, or we can find some big N such that for all little n greater than or equal to that big N, it's less than epsilon. So again, the first thing we're going to do is just manipulate algebraically this absolute value. So remember what we're going for. The things that we know something about are the differences between an and a and the difference between bn and b. So at the moment, this is in a difficult form because it doesn't have any of those. But we're going to perform a cool little algebraic manipulation to put those things in. So this is how. So we're going to add and subtract the same thing. So we'll subtract off an times b, and then we'll add it back on, an times b minus ab. So I hope you agree there's no difference there. But now what we can do is apply the triangle inequality to this as our x and this as our y, to say that this is less than or equal to mod an bn minus an times b plus mod an b minus ab. So if we can make this thing less than epsilon, then by transitivity this thing and indeed this thing will be less than epsilon. So that's our new target. Make this thing less than epsilon. That's a horrible epsilon. There we go, a little bit better. Now, let's just factor some things out of those absolute value signs. So we're going to factor out the an here to rewrite this as mod an times mod bn minus b. And we're going to factor out the b from that second one to make it mod of b times mod an minus a. And we are trying to make this less than epsilon. So we can use the same trick as we did previously, because we know we can make these indefinitely small, so we can make them as small as we like. So that's looking very hopeful. This is again absolutely fine because this is just some constant value, so we can take account of that. We're just going to have to make this epsilon over 2 times mod of b. The more difficult thing is this, because this isn't just a constant. This is something that's going to change. This is a term that is going to change with each of the n values. However, we can still fix this because there is a maximum value that all of these can be. So if we use that boundary and put it in there and make the inequality still hold true with that, then it will certainly then be true that without it, it holds true. And let me explain better what I mean by that, because that sounded like meaningless garble. So this sequence, an, converges to A, it's a convergent sequence, that ends up meaning that the sequence is bounded both above and below, and therefore its modulus has a maximum value. So let me convince you of the fact that it's bounded firstly. So because it converges to A, I can then apply the definition of the limit to, let's just say, set epsilon equal to 1 and consider this interval a plus 1 to a minus 1. Now, because of the definition of the limit, it means that there is a point, there is a big N, a term in that sequence such that for that term and all the terms afterwards, they are all inside here. So we'll have that a big N and all its terms afterwards, so all the a little n, where little n is greater than or equal to big N, they're all going to sit inside there. Therefore, that's beautifully bounded. They are bounded above by a plus 1 and they're bounded below by a minus 1. So they certainly are bounded. And then all the terms prior to it in the sequence, so all of these terms that might not have been inside that epsilon equals 1 interval around a, well, there's only finitely many of them. So they might be dotted around, you know, they might be here, here, these little dots are representing them, but there's only finitely many of them, so you can just look at what's the maximum and what's the minimum of them, so it will end up being bounded. It won't end up that suddenly you could have ones going off to infinity. So for instance, an example of a sequence that isn't bounded would be the sequence n. This is the sequence 1, 2, 3, 4. That has no upper bound. It has a lower bound. 0 is smaller than all the terms of the sequence, but it has no upper bound because the terms of the sequence are going off and off and off. And this doesn't have a limit. But because we're not talking, thankfully, about a sequence like that, we're talking about a convergent sequence, all of the infinite number of terms after this a big N are all trapped inside this little interval. So there's no chance of it suddenly going off and becoming unbounded because the only terms that are outside of this bounded interval are a finite number of terms, and a finite number of terms can't go off and be unbounded. You know, they're dotted around. There's a finite number of them. You can find out which one's the maximum and which one's the minimum. So for my sequence A, I can then find you what is the maximum. Well, actually, I should be a little bit more careful. I can't necessarily say what the maximum is because I can give you an example. For instance, I could say my sequence AN was equal to negative 1 over n, so the negative version of the harmonic progression. That would be minus 1, minus a half, minus a third. Now, this sequence doesn't have a maximum. It is bounded, but it doesn't have a maximum, you know, because the numbers are progressively getting bigger and bigger and bigger towards 0, but there is no maximum term. However, there is still a number that is bigger than all of them, so there's going to be some upper bound. So we'll do it in terms of that. So because my sequence is convergent, I can say there is some upper bound and there is some lower bound. So u is going to be bigger than every single one of the terms. So I'll write this. For all n is an element of the natural number, as u is greater than or equal to all of my terms, and L is less than or equal to all of my terms. So I've got some lower bound here on the picture L, and some upper bound here on the picture. Now, all I then need to do is take the absolute value of u and the absolute value of L and ask which one is bigger. And it might be the case that the lower bound is bigger. It might be a negative 100 and the upper bound might be 50, in which case mod of negative 100 is bigger. But one of them will be the maximum, and we'll call that number n. And now I am going to replace this thing here with m, because that's the maximum it could ever be. I am absolutely sure that mod of an is going to be less than that number n, because that is the biggest one of the mod of the upper bound and the mod of the lower bound, and all the terms of my sequence are between the upper bound and the lower bound, so they have modulus smaller than this value n. And this is how I'm going to get rid of this awkward problem that I've got here. So now I'm going to write another inequality. So mod of an times mod of bn minus b plus mod of b times mod of an minus a is going to be less than or equal to this m times bn minus b plus mod of b times an minus a. So that inequality comes from this inequality here. I'm just going to actually put a slight correction there. That should be less than or equal to, because actually we said that this upper bound was greater than or equal to an and the lower bound was less than or equal to an. So it could have been maybe that the upper bound was the bigger of the two and it was actually equal to the maximum value of the sequence, in which case m would actually equal one of the values of the sequence, so it would need to be less than or equal to m in general, this inequality. So you get this from this quite simply by multiplying both sides, firstly by mod bn minus b. That's a positive number, so it doesn't change the sign of the inequality. So you then have this thing is less than or equal to this thing, and then we've just added on this to both sides. So from that and basic ordered field manipulation of an inequality, you can get this. Now, if I make this thing less than epsilon, by transitivity, I will then have that this thing is less than epsilon. And this is how this argument becomes so much more complicated, because if you remember, the original thing we wanted to be less than epsilon was this thing. We've said that this is the same as this thing is less than or equal to this thing, and now we're saying this thing is less than or equal to this thing. So if we make this thing less than epsilon, then we'll have finally, by transitivity, that this thing is less than or equal to epsilon. So that's how we're going to proceed. So now all we have to do is apply the definition of convergence of the sequence of A and the sequence of B, and we just have to pick our epsilons cleverly. So for this sequence B, we're going to make the epsilon equal to epsilon over 2 times m, and for the sequence A, we're going to make the epsilon equal to epsilon over 2 times mod of B. So these things will be less than these, and then you can see that the m will cancel here, the mod b will cancel here, and you'll overall get that this is going to be less than epsilon over 2 plus epsilon over 2, i.e. it will be less than epsilon. So again, just to put a little bit more on this, so because Bn converges to B, there will exist some big M1 is an element of the natural numbers, and I really should have begun with A to keep the same pattern as we had previously, but never mind, it doesn't matter. There exists a big M1 is an element of the natural numbers such that for all little n is greater than or equal to big N, 1 mod of Bn minus B is less than epsilon over 2m. And then for this one, because An converges to A, there will exist some big N2 is an element of the natural numbers such that for all little n is greater than or equal to N2, mod of, and I've almost written the wrong thing again there, so let's get rid of that. Mod of An minus A is less than epsilon over 2 mod B. Then all you're going to do is make the real big N equal to the maximum of, going to get rid of that bracket and replace it with a brace. Oh, gone horribly wrong. The maximum of these two, so take M1 and N2, one of them might be bigger than the other, take the maximum of them, and then if you go to that term of both the sequence Bn and the sequence An, then both of these things will hold true. So, therefore, for big N, we can say that for all little n greater than or equal to this big N, mod of Bn minus B is going to be less than epsilon over 2m, and mod of An minus A is going to be less than epsilon over 2 mod B. So we now just have one final bit of manipulation to get the inequality we want. So we'll start by multiplying both sides of this inequality by m, and we'll then have that m mod bn minus b is less than epsilon over 2. We'll also multiply both sides of this inequality here by mod of b to get that mod b times mod an minus a is less than epsilon over 2. And then to arrive at this inequality, I suppose in full rigour, what we'd need to do is add this thing onto both sides of this inequality. So we'd get m times mod bn minus b plus mod b times mod an minus a is less than mod b times mod an minus a plus epsilon over 2. And then all we'd do is then take this inequality and add epsilon over 2 onto both sides. So we then have this thing plus epsilon over 2 is less than epsilon over 2 plus epsilon over 2, which is epsilon. And then by transitivity, we'd have this thing is therefore less than epsilon because this thing is less than this, and we've manipulated this so that this is here. So we'll then have that this is less than epsilon. So we'd then have overall that this is less than epsilon, which is as desired. So overall, we've shown that this thing can be made less than epsilon, and as this thing is less than this thing will be less than epsilon for that big N, and as this thing is less than this thing will be less than epsilon for that big N. So we've done the proof. So final one now, so I think we'll go over here. So it's the most difficult, but we've built up in such a way that a lot of the tricks that we've used in that previous one for the product we'll use again here. They're just slightly more complicated. So it's been a beautiful build up to this final proof. So we want to prove that an over bn converges to a over b. And remember the caveats are that bn's cannot ever equal 0, and the limit of the sequence b of n, b, cannot equal 0. So same style of proof, so let epsilon be greater than 0, and we want to show that there exists a big N such that for all little n greater than or equal to big N, the mod of an over bn minus a over b is going to be less than epsilon. So we want to try and manipulate this in terms of things we know, because we know the limit of an and we know the limit of bn, so we want to get this in terms of things like mod an minus a, mod bn minus b, using the triangle inequality again. So we're firstly going to get it over a common denominator, so some little algebra firstly. So an b minus a bn over bnb. So that's fine. So we can rewrite this now as mod anb, whoops, get rid of that, minus abn. So absolute value properties, so we can rewrite this like so. And we're now going to try and do something to that numerator to get it in a form, as we've done previously, where it has an minus a or bn minus b appearing in there. So we're going to add something in and subtract it off. So this is equal to mod an b, and then we'll put in minus a b plus ab minus abn. So that looks as though it's going to work perfectly, and then it's divided by mod bn divided by times mod b. So again, I've just split that absolute value up. And now, by the triangle inequality then, we have that, not like that, we have that mod an b minus AB plus AB minus ABN is going to be less than or equal to, we're using this as our x and this as our y, it's going to be less than or equal to mod AN minus A times mod B plus mod A times mod, and then I'm going to rewrite it as mod Bn minus B. It doesn't matter because of course mod of B minus Bn is exactly the same thing as the mod of Bn minus B, so multiplying by a negative sign doesn't affect the absolute value sign. So that's the triangle inequality applied there, and also some basic properties of the absolute value function. And then because this is less than or equal to this thing divided by this thing is going to be less than or equal to this thing divided by this thing. This, after all, is a positive number, so its multiplicative inverse is a positive number, so we can multiply both sides of this inequality through by that, and we don't need to flip the sign of the inequality. So we'll therefore get that the thing that we want, which is mod ANB minus ABN over mod BNB, so I've just written this thing out over here again, is going to overall be less than or equal to, and now I've split it up, so we'll have mod of B times mod of AN minus A divided by mod BN mod B plus mod A times mod BN minus B over mod B times mod Bn. And we can see clearly that the mod B in this one over here cancels with the mod B there. So our strategy here is again to make this thing less than epsilon, and then by transitivity the thing that we want will be less than epsilon. So this is looking hopeful because again we've got these things here which we know we can make as small as we like. Mod A and mod B are not problems, they're just constant values, so they're just going to mean we have to select how small we want this more carefully. The problem is again these mod BNs. They are like what we had in the previous problem where we had mod AN, and the problem is that these terms are changing and therefore the value of mod BN is changing. And the way we got around it previously was by saying, well, because the sequence converges, it's bounded, and therefore there is some value, big M, that is greater than or equal to mod AN for all the ANs. And therefore, if we can replace mod AN with this and make this new expression with M replaced less than epsilon, then our original expression with AN in will most definitely be less than epsilon. We need to do the same thing here, but it's now going to be slightly more complicated because we're now dividing through by mod Bn. So instead of being worried about how big Bn could get, we actually need to be worried about how small Bn could get, because for small values of mod Bn, that's where it's going to be making these things very big. So again, we're going to replace mod Bn with some number that is always going to be smaller than it. So how do I know such a number exists? It's because of the initial restrictions that I put on this sequence B in order for this property to hold, and because I know that B converges. So I know that this sequence converges to some value B, and I know that B is not equal to 0. That was one of the initial criteria for this, this rule to apply. So here is 0 and here is B. So what I can now do is look at this distance between 0 and B. So it's equal to length B. And I can then take, or the absolute value of B more generally, because B might have been a negative number, but in this case I've put it on the right-hand side of 0, so it's drawn as a positive number, but it could have been a negative number. So in more generality, the distance is going to be mod B. So what I can now do is half that and take an epsilon interval around B of size mod B over 2. So this is going to be B plus mod B over 2. and this is going to be b minus mod b over 2. And then because I know the sequence converges to b, I know that there is then a big N such that all the terms of the sequence from that term and onwards are inside this interval. So b big N here, and all of its terms onwards are inside there. So that means that, for instance, b minus mod b over 2, this number here, is actually size smaller than all of the terms, all of the infinite number of terms that are inside of here. Or more generally, because that would only apply if we were talking about b being a positive one. If we were talking about a negative one, it would obviously be the other way round. It would be this one that would have the smaller absolute value. But the important point is that by doing this argument, whether it's on the left or the right of 0, I can find you some number here, which we might call, what shall I call it? We'll call it little m, because it's going to be tiny. Some number little m such that its mod is smaller than or equal to the mod of all of those bn's. So I can find you this little m such that it's less than or equal to the mod of all of the little bn's for all little n that is greater than or equal to big N, of course. So that's only applying to all of these ones onwards. But of course, that's the bulk of the problem over, because that's the infinite sequence. Before that, there are just a finite number of terms, which again are dotted around. So I can just have a look at all of those terms. Some of them might actually be smaller than the little m I've got, but that's okay. I just need to then find another little m that's even smaller. And the reason I can do that is because of the other criterion that we had, which is that none of the terms of the sequence are equal to 0. So none of them are that small that they're actually equal to 0. So they're all either to the right or left of 0. And there's a finite number of them, so just look at them all, and you will then be able to find some number that's actually of size smaller than all of them. So I can replace this then. I can find a little m such that its size is less than the mod of bn, less than or equal to the mod of bn for all n is an element of the natural numbers. So that's because of the fact that this sequence converges to b. B is not equal to 0, and none of the terms of the sequence are equal to 0. Now, because this holds true, we can now do some basic manipulation. They're both positive numbers, so they both have multiplicative inverses, and those multiplicative inverses are also going to be positive numbers, so we can multiply through both sides by the multiplicative inverses, and we then get that 1 over mod of bn is less than or equal to 1 over this m. And now we can use that to create a new inequality, which is factor this out here. So imagine factoring this out. So we've got 1 over mod bn times, and then we've got mod an minus a plus mod a over mod b times mod bn minus b, like so. And those are just normal brackets rather than, they look like absolute value signs, but they're just meant to be normal brackets. So what I'm now going to do is multiply both sides of this inequality by this thing here, and then multiply out the brackets, and what I'll then get is that the thing that I originally wanted, an minus mod a over mod bn plus mod a times mod, times mod bn minus b over mod b times mod bn is less than or equal to mod an minus a over this value m plus mod a times mod bn minus b over mod b times n. So here we go. If we can make this modified thing less than epsilon, then this thing will be less than epsilon, and then it will carry on back down transitivity to whichever initial thing we wanted. Oh, here it is, isn't it? So this thing will then be less than epsilon. So that's our new task then, to make this thing less than epsilon, and now this is doable because this is just a constant value. So we're going to make mod an minus a less than epsilon over, I've made a slight mistake there, let's rub this out. So it will need to be less than epsilon times m over 2, and mod bn minus b will need to be less than mod b m epsilon over 2 mod a. So again, because this one converges to a and this one converges to b, there will exist some big M1 such that for all the terms from that term onwards, for all the terms, this is true, and there will exist a big N2 in this one's case such that for that term and all the terms onwards, this is true. So now just take whichever one is the maximum, so that big N equal max of N1 and N2, and then it is true that for all little n is greater than or equal to big N, that we have both of these inequalities. And now we just need to manipulate them so that we overall then have this inequality. So the first thing to do is just multiply through by a few things. So we'll manipulate this one. So we'll multiply through by the multiplicative inverse of m to get that mod an minus a over m is less than epsilon over 2. And then for this one, we'll multiply through by mod a over mod b times m to get that mod a mod bn minus b over mod b m is less than epsilon over 2. And then the same trick as previously, so we're going to take this one, let's say, and add this thing onto both sides. So we'll then get an minus a over m plus mod a mod bn minus b over mod b times m is less than epsilon over 2 plus this thing, so plus mod a mod bn minus b over mod b m. And then we'll take this second inequality, this one here, and add epsilon over 2 onto both sides. So it will become epsilon over 2 on that side, and this one side will become epsilon. And then we can apply transitivity. This is the same thing as this, so this, therefore, is less than epsilon, which is the result as desired. So we've got that that inequality is true, which then implies that this thing is less than epsilon, which then, going all the way back up, implies this thing is less than epsilon, which then implies that this is less than epsilon as desired. So we have found a big N such that this is true. And since we did it for a general epsilon, it then holds true for all the epsilon greater than 0, and hence we've proven it. So we'll end there. Thank you for watching.